So for the last presentation of the day, I'm going to talk a bit about PDF databases. The emphasis I'm going to talk about is for data mining within the database, some examples over here. Then as time permits, we'll hit on, if we can, just a couple comments about the phase ID, and if time permits, a little bit of phase ID with the JADE software. So that's what we're going to try to cover in the hour plus that we've got here. Okay, so one of the things is that, as we've discovered today, the wireless, it's good, it's not good, it's good, so I don't know that you'll be able to follow all the time. Sometimes it's in, sometimes it's out. But what you do have is information, I guess, now has been sent to you that says how to get to the database. It's a web access, so you don't have to download it. It's web access. You should have a username, password, I believe now, and you can access, and it's for the next 2 weeks you have access to the database. I'm here for the next couple of days, obviously, as well, so if you have questions, you can ask me as well. I'm going to be using database on my desktop because I don't know if I'm going to be in or out, and we'll proceed as best we can, okay? All right, so just to get started here, there is a web access. You'll type in your username, your password. On the desktop of the web access is the database, PDF5 Plus or JADEPro software. And you'll be following a bit some of the examples I'm going to have back and forth between my PowerPoint and the actual database itself. So let's talk about where we are. We're interested initially in talking about the PDF5 Plus database. Presentation earlier today talked about some of the basics of the database itself, and we talked about the database form. Now, in the form itself, you do have multiple components that you can use for your data mining. The different databases I showed earlier, whether it's ICDD data, FIS data, CSD data, we have NIST data, minus Pauling file, and then some ICDD crystal data as well, all are included. When you do a search, it assumes that you're searching through all these databases, but if you want to search for a specific one, you can just tag it, okay? Now, the other thing you'll see in terms of the data you're analyzing, sort of in the upper right, there's an icon that says all data. That means you're looking at all 1.1 million entries. But if you're just interested in inorganics, you can click on inorganic emphasize. If you want to just search the CCDC data, organic emphasize, or again, you can search everything. Now, in the inorganic emphasize, it includes ICDD data for what I would call your commercial or commonly found organics. So they're not left out. They would be part of the search. Question earlier about, can you do things like ambient? You can say yes to ambient or non-ambient. So the ambient for us is either temperature or pressure. We have a number of subfiles that we're going to go through. And I mentioned earlier about the quality marks, and I'm going to give another example of that here. We talked about all the entries are reviewed. It's a curated database. Here was a paper for publication of beta-carotene. The powder pattern, you typically have just this broad amorphous type pattern. But once again, we see some very sharp peaks. And the authors of the paper were attributing these peaks to the crystallinity of the beta-carotene, okay? The only problem is this is the pattern for beta-carotene, and there are no sharp peaks in the material there, okay? And this pattern is something we've collected as part of our polymer program, and it is in the database. So what are those peaks? That's the sample holder, okay? And when you don't review these patterns, this is what gets into the database, and this is the type of thing that people are doing and making claims about degree of crystallinity of their sample. So do be careful when you're looking at data like this. Okay. All right. So first thing is, when I look at the database and the search form, one of the things you can do is you can say, I'm interested in a very specific PDF entry. For historical purposes, the term PDF cards is still used, but keep in mind it's not a physical card anymore. So you can take a particular entry. If you happen to know the PDF number, you can enter that entry in there, and you can look at the powder diffraction file data for that. And you open it, and the PDF entry itself will open and take a look at that. So we're going to do that exercise together, okay? So the entry we're going to look at is 00, which means it's ICDD originated data, set 74, and entry number 1030, okay? So when I look at the database, let's take a look at something here. One of the things that this is helpful, particularly for people who need readers to see something, you have a preferences icon here, and with that preferences icon, you can adjust the font size. So the default is 100, you can go up to 175, so it just blows the image up. And obviously, if you had a large monitor, it's really nice when you can blow up the text and the font and everything. So just for something you don't have to squint and try to see what's going on. The laptop, maybe not quite as convenient, okay? All right, so we said we were going to open up a PDF entry. So in the upper left-hand corner where it says PDF card, we said that it was 00 data, which means it's ICDD originated data. We said it was set 70, so 070. And then we said it was entry number, I believe 1040 was our entry number. And when we've got that, we can open up that PDF entry. Perhaps I hit the wrong one. Apologies if I did. 1030. Apologies. But okay, fine for the moment. 1040, this is a organometallic type phase, basically principally organic pharmaceutical phase. If I'm interested in 1030, I simply would just close this particular entry, and I would go back up to my PDF entries and go 00, 070, 1030. Well, where am I?
No.
Okay, thank you. I could say I was making sure you're paying attention, or I could say I wasn't paying attention.
That's the fun.
Okay. 070, that's fine. I'm just typing here on my laptop. 070. And then no, that part I understand. And 1030, 030. Okay. Telling me that I pay attention to what I'm doing here. Oh, 0741030. Yay! Okay. Sorry about that, folks. Okay, so what we have here is a PDF entry for the mineral sodalite. Okay? And as we look at what the options are here, the initial component is the list of Ds and relative intensities, relative to 100, okay? And you have 2 theta values. Now, we talked about earlier that you had the option to change your wavelength, okay? And when you do that, you can either say, I'm working with a different radiation in my laboratory, so I'd like to change the wavelength here. I'll also go back up to my preferences icon that was up here. And under diffraction pattern, I can permanently change so that all of my PDF entries, this particular wavelength will show up. So for example, someone who's working with a lot of iron in their laboratory might be using cobalt radiation as an example. So you might want to go to cobalt instead of copper as your default, okay? Okay, so I have my list of D's, I's, and you'll notice a few of the D spacings are highlighted in bold. Those are the entries that are the 3 most intense in terms of diffraction peak intensity. but you had the list of your 2 thetas. But suppose I did in fact change my radiation to silver. And what's going to happen is the 2 thetas will change automatically for you. Despacings are fixed. That's a function of your unit cell, okay? But the simulated plot or raw data plot, whatever you happen to have, will in fact show up with a change in the 2 thetas, okay? You can go back to your default if you wanted to. In addition, let me show you one other component here. There's a tab on the left-hand side that goes to cross-reference, and that means there are other entries in the database that are matching very close to this particular entry, and you can check those out as well. When you're checking out one of those entries that has the calculated pattern, and I'm just going to click on the one of 04008, and I click on that, what will happen is I can open up that PDF entry, and this is calculated from a crystal structure. Okay, that's fine. We talked about the question earlier of what's the best intensity. Keep in mind, most of the data that's submitted, experimental data submitted, is typically received as peak intensity data. But when you have the calculated pattern, you can decide if you want it as peak intensity and with a fixed slit or variable slit that would be on a powder diffractometer. But you also have the options it shows here to have the data displayed as integrated intensity. So again, depends on the particular type of experimentation you're doing. You can use peak or experimental, okay? The other thing, when you have the calculated pattern, you also have the option for neutron diffraction data, okay? And in this case, you can either use constant wavelength. Now, the default number it throws in there is the equivalent of copper radiation wavelength, but you can put any wavelength in there you want if you happen to be working at a constant wavelength source. Typically today, it's going to be time of flight. So there is a time of flight option for simulating the pattern, and you can look at that, and you can see what the time of flight pattern would look like for this particular phase, okay? Now, on top of that, one of the things that's nice about the time of flight pattern, if I open up this, what we would call the simulated pattern here, you have the option under the pattern that we're working with here. You can add isotope substitution. So if the material typically could have isotope substitution, which will significantly or can significantly change your intensities, you have the option to include which isotope you're working with if you're doing neutron data, okay? But our focus today is going to be principally laboratory type diffraction systems. Okay, let's go here to the start with the PDF tab. So we mentioned that you had the despacing intensities. If I look in the sort of top region here, I have some options, including I can look at the 3D structure. If you have the atomic coordinates, okay, you can move the atom, the unit cell around. You can add unit cell numbers if you want to see what happens when I have stacked unit cells, for instance, and maybe I'm looking for some porosity or something that's in the particular material. I can zoom in. I can zoom out. I can also spin it around if you like to make it look nice. You can spin these things around. And there is an option here that, in addition, you can store the pattern if you'd like to. You can go to File. I want to export this pattern. And you have some options here. You can just export the still image, but there's also something called animated GIF. If you want to put that circling structure in your slide when you start your presentation, people like, oh, the molecule spinning around, you can do that as well, okay? All right. My personal experience working in an industrial environment, is managers love that stuff. They love colors and they love molecules spinning around. Okay, all right. So you have the option with the structure. Now, under the structure tab, there's also BFDH extension. And with that, you can essentially look at some of the issues that potentially are around the lattice planes. You can relate lattice planes to the structure itself. When it's cubic, like this material, and you're looking at the 110 family of planes, everything's colored the same. But if you're looking at a non-cubic system, it'll color the planes differently. But it helps you, gives you some sense, in particular, as you might start to look at things like orientation of crystals or particles. Okay, so just another option available in terms of doing your analysis when you're looking at the structure. And so this is just an extension on that. Some of the other things, you have a bond length extension. And in this case, if you're interested in getting an idea, here's the bond length in this particular material between the sodium and the chlorine. But what's the distribution of all the entries in the database? And you can see how you compare to that. Are you outside the norm? You're in the norm? Where are you at there? Again, sometimes when people are doing some structural work, they just like to get a sense, does this make sense or not for this kind of bond? Maybe not as unusual in inorganics and organics. It's quite a bit. Someone says the bond length is unusual. The bond angle is unusual. Okay. But our focus here is on the inorganic materials in this case. A couple other things here. Now, in this particular pattern, there was raw data. The author made available the raw data, and if it is available, we are putting raw data in the powder diffraction file. So you can compare your pattern to what someone else collected to say, does it look the same or does it look different? You also have the option to, on every entry, even if the structure has not been determined, based on the despacings and intensities, you can simulate every diffraction pattern. The key here is you have to decide, what do you want your profile to look like? Now, the default here is just a pseudo-void profile, okay? You do have some other options. You can have just a modified Thomson-Cox-Hastings, Gaussian-Lorentzian. One that's kind of nice just to get an idea is one called crystallite size. If I click on the crystallite size profile, what it will do is it will let me simulate what the diffraction pattern will look like as I change the crystallite size. So if you're looking at nanomaterials, and you're saying, hey, I think I have a crystallite size of, 25 angstroms, then I'm going to have some very broad diffuse peaks here, okay? That also allows you to put a sort of a variance in there because it's not 25, there's always a distribution. So depending upon that distribution kind of changes your tailing a little bit. But keep in mind, this isn't a felt refinement. This is just giving you an idea of what the simulated profile would look like for a certain crystallite size. But it's a nice way just to get an idea of what's going on. I can go back to, say, for example, my pseudo-void profile. We also have a March Delas function you can use in the simulation and say that suppose the material I'm talking about here, it's a little bit platy in nature or it's needle-like in nature. What's that going to do to my diffraction pattern? So we've heard some comments today that one of the problems for powder XRD is preferred orientation, and sometimes that can make it difficult identifying materials. This just gives you an idea of what's going on, and if you say, well, I've identified what I believe is a phase, but my intensities don't look right, this is a quick idea before you go in to do some kind of profile fitting. Okay, just a couple other things here that you can do when you're looking at the PDF entry. Every entry can have a simulated ring pattern. Again, it's just taking the despacing, the 2 theta, the relative intensity, and you can change what you would imagine is your sample to detector distance, depending upon the geometry that you're using, what's the radiation you're working with. You can put in a crystallite size effects to make the the rings somewhat broad or somewhat narrow. Sometimes if you want to highlight low intensity rings, you might go to square root or log intensity. There is an orientation distribution function here. It works well for cubic material. If you do ODF on a triclinic, even on a very fast computer, start it, probably get your cup of coffee, come back, it'll be done. Okay, I mean, it's just a lot more calculation when you're doing an ODF for something that's like a low symmetry system. Okay. And then in addition to that, you can say I'm working with an area detector, but many people now in the powder world and powder diffractometers are working with strip detectors, so you can simulate what the strip pattern would look like based on if you're using it in what we would call 2D mode. Okay? All right, just a couple of things here as I'm looking through this. We can simulate a selected area electron diffraction pattern. And in this case, you can say, I've got a particular pattern here, and you can, in fact, if you wanted to, you can import a pattern, and by importing it, you can overlay to see, does your pattern match? You can change the camera constant to the camera length, and you can decide, maybe I'm not looking down the 001, maybe I'm looking down the 101 zone axis, and it will recalculate the zone axis for you. Okay, we have an enhancement of this, and we call it the SAD extension, and in this case it's a little bit more tied into the crystallography itself, and you can say, well, here is my crystal structure, and if I'm looking or changing the orientation of the crystal, what's it doing to my SAED pattern? And you can say, well, I'm not sure, but I think I'm looking down 112, and I can say, what will that look like in terms of my pattern there? So just another way to enhance the ability to not just do powder diffraction data, but you can also look at electron data as well too. And just one little final catch here is that same thing with the electron backscatter. You can look at backscatter patterns as well, and it's the same kind of thing. So you can see what your Kikuchi line should look like. You can compare this to your data, look at the orientation, etc. Okay. So years ago, when someone said I was purchasing the powder diffraction file to do my phase ID on my material, that was correct. You had D-spacing, intensities, maybe HKLs if you knew the unit cell, maybe a little bit of extra data in there, but now, of course, with it being in an electronic format, it's expanded in its capabilities. A couple of things just to pay attention to. You can click on references here, and this is kind of handy because sometimes somebody gets a match for something, and they say, I wonder how they made their sample. I wonder how they did their data. We're working, and it's kind of working now, newer issues and journals, it's easy to include the DOI. We're working backwards on the 85 years of data that's there to try to get more DOIs in here so that you could at least see what the literature abstract was, and then if your institution has a subscription, you can get that particular article. But sometimes it's quite handy because experience has been that, we'll get a little cryptic information on what someone did to get the material, but it doesn't describe it as well as what's in the paper. And then finally, I'll just add that this is a good thing to do when you're looking at a new entry that you haven't seen before, haven't worked with before, the comments. So there's a lot of different comments. Sometimes it's structural related. Editor reviewed this particular entry and found that it's a pretty good structure, but maybe the thermal parameters or not all the thermal parameters were complete, or we found some kind of atom overlap, and be aware that these are some of the things here. But this is a good thing just to be aware in terms of when you're looking at PDF entries. Okay. All right. So let's go to our presentation for just a moment. I just want to add a comment on some things. Talk about putting raw data in the database. Now, admittedly, if you said, hey, we ran a lab 6, we put that in the database, that's good, that's nice. Your lab 6 will probably look similar to this lab 6. It's pretty straightforward, nice sharp peaks, good peak positions. But there are materials that just do not have very nice diffraction patterns, and yet it's the real pattern, okay? And historically, and basically for phase identification, you search on a DI list, despacing intensity list. But here's an example of a clay. So halloysite 10A clay, and it's called 10A because the first peak is close to 10 angstroms in spacing. And if you look at the pattern here, you'll notice that it's got this region of asymmetry, and the asymmetry is on the high angle side. Now we know in diffraction peaks in a Bragg-Brentano instrument tends to be at low angles, some asymmetry on the low angle side. You've got this axial divergence issue, but this is a structural thing going on here, and a lot of it has to do with, in clay, some of the misalignment of the clay layer, okay? And there's some disorder, and so you get this asymmetric profile. If you were searching on just a DI list, you would never get that profile information. So a big effort at the ICDD has been getting raw data, particularly for polymers, disordered materials, nanomaterials, to help with the identification. So when someone runs a pattern in their lab and they say, well, I know it's 10A clay, but why does my pattern look like this? We're trying to help with the identification, okay? So we're putting a lot of clays in the database. Polymers, this is Nafion polymer. It's used in fuel cells. And in the case here, the issue is that at low angle, there is sort of a superstructure, an ionomer component. And then at high angle, you've got your typical wide angle amorphous type polymer. Well, if you use just the DI list, you wouldn't really differentiate between the ionomer polymer part. So we put patterns like this in the database. Nanomaterials, again, to help understand why, a nanomaterial, yeah, I have the peaks where I should see cubic zinc sulfide, but the peaks are broad, okay? And so again, when someone says, I have a pattern that looks like that, it's helping with the ID. And even to have a little bit of fun, we even have a pattern of water in the database, okay? Water does have a diffraction pattern. It's not sharp peaks, but there is some order in even water. And so putting a pattern like that in the database, well, it's there, okay? And I will say, it wasn't simple to put the pattern in there because, you're collecting your data, and what's water want to do? It wants to evaporate. So, you got to be collecting the data at a speed that you can get a good pattern, but yet enough good data, all right? All right, so let's go back to our search form again. And one of the things that you can do is you can look at periodic table, okay? So the periodic table is probably the most popular search. So let's go to that for a moment here. Okay, so I've got the periodic table, all right? And you have some different types of search. You have a Boolean type search. You have what we call a yes, no, maybe search. And then you have a compositional type search. So let's look at the Boolean search for a minute. So Boolean has Boolean operators, and, only, or, just, and you can even use a not, okay? So let's look at and, okay? So I want to know what phases are in the database, and I'm going to go up for the moment and say inorganic emphasized. I don't need to search all million. I only need to search 500,000, okay? So there's still a lot of entries to search, right? And I want to know about iron, cobalt, oxides. So I'm going to click on iron, cobalt, and oxygen on my periodic table. Now you'll see at the very bottom right, there's a little hint as to what you're seeing. There's 3,054 entries without having to display all of them. And we do that because what we would find is people would do a search, they'd have to open up, look at all the entries. Oh, that's not what I wanted. This gives you a quick idea, am I in the right ballpark or not? But for the moment, let's say that I'm going to open this up. How do I open up this search? In the bottom left, you'll see a search icon. Click on that. Now, if you're using the web search, keep in mind it's going to move just a little bit slower. You're going from Italy to California, back to here, and in California, they're probably not even out of bed yet. No. There's just a little bit of delay, okay? All right, so I said cobalt, iron, and oxygen. First one looks okay. I come to my second search item, and I see a hydrogen. I see a barium. What happened? Well, in the Boolean search, I said it had to have these three elements, but I did not say others couldn't be there. So that's the Boolean search, and, okay? So in all of these entries that show up, they all will have cobalt, iron, oxygen, but they may have other elements, all right? So what do I do? Well, let's close this. So there's a red X here in the search box. And I'm going to change my operator to only. In this way, it has to have only those three elements, okay? And now notice in the bottom right, I'm down to 177 rather than over 3,000. So I'm going to click on my search again. And now I can go through and scroll through here, and I will find only those three elements present in my pages. Okay? Now, the composition may be different. We'll talk about how you can set that in a moment. But you can see now, we said we had 1.1 million entries, inorganic emphasis, 500,000, cobalt, iron, oxygen, and I want only those elements. I'm now down to 177, okay? And there are other things we can do to narrow this down. We're going to do a subfile search in a moment to show how you try to do data mining to get yourself to a centered group, okay? All right, just a couple things. So right now I've got the data here. And when it shows up, it will show up in order of PDF entry numbers. So it's the 00 data first, then 01, 3, 5, etc. Okay. But if I wanted to say, show me something about quality marks, and I click on the quality mark column, it will rank order them from the highest quality, next highest quality, down to the low quality, okay? So remember our green, yellow, red from earlier? Green, go. Yellow, if you're driving, what's yellow mean? Hurry up and go. Caution. Red means, pause a second and let's make sure we know we're okay with that entry. All right? Okay. So I'm going to close this again and just show a couple of the other operators here. If I said or, the number's going to go up again, because what I'm saying here now is it only needs to have one of these elements. It could be iron, could be cobalt, could be oxygen. Well, there's so much oxygen and everything, you got 330,000 hits now, mainly because of oxides, but it could be all kinds of oxides. And then the final one, called just, means that it's those three elements, but any combination of just those three. Or it could be iron cobalt, could be iron cobalt oxide. So it could be multiple mixing of these particular elements. So there's 1,200 combinations there. So you can decide how specific do you want to be. Okay? So that's your periodic table search. Okay? All right. So in our discussion here, we have the search form, and we have an option called subfiles. Why do you use subfiles? Example here, suppose you had a bowl full of jelly beans. What are jelly beans? Well, how do we typically separate jelly beans or look at jelly beans? By the color, right? You see some purple, some are red, some are yellow. And if I had the whole bowl and I need to go through and search out the different colored jelly beans, well, that could be a lot of work. So what if someone did that for me? So we take the bowl of jelly beans with all the colors mixed together, and now someone separates them out into the different colors the database is similar. We went from all data entries to sub-files of similar material types, battery materials, pharmaceutical materials, cement materials. And by doing that, you can now concentrate on fewer entries that you want to search through. But even within a particular set of entries, there's even anomalies. Okay, so here's an example of maybe you're looking at minerals, but is it gems? Is it natural minerals? Is it synthetic minerals? So you can break it down to subclasses even further. So that's what we've done in the powder diffraction file. So we're going to do an example here of how to look at cement and hydration products, and in particular, narrow down our focus to a specific phase type, okay? So let's do the demonstration here. Okay, so the first thing I want to do is I want to clean up what I just did. At the very bottom, you'll see the search that we had used before. I'm going to do reset all. Now you'll notice my periodic table tab turned red. When you start using the tab, it turns red to let you know it's active. I'm going to hit the reset all. So now I've cleaned out everything, okay? And we said that we were going to do a cement hydration product search. So I'm going to click on that subfile. And you'll notice the subfile heading now turned red, meaning it's active. And there's 1,636 entries that are in this particular subfile. Now I say, well, you know, that's nice, but I'm really interested in calcium silicates. So I'm going to click on only for my elements, my Boolean search. I'm going to go calcium, silicon, oxygen. Okay, down to 120. All right. And I'm actually specific I'm interested in a specific calcium silicate. The cement people like to use these letters with numbers. So there's one called C2S. It's not a dicarbon sulfide. It's, 2 calciums, a silicon, and then the appropriate oxygen to go with it. So I'm going to go to another tab now, and it's below periodic table, and it's called formula. And in the formula, I have some options. I can say any formula, chemical, structural. Structural is kind of nice if you're looking at organic materials. You kind of put structural components there. But you have multiple ways. Again, you can narrow down your search, and it can contain the elements, contain a phrase, or it can be exactly a certain composition. I'm going to leave it with any formula, contains the elements, and I'm going to put in here Ca2. So I want a Ca2 containing phase, okay? And we see now that we're down to 61 entries, okay? A couple other things. I'm going to want to do some kind of refinement work, so I want atomic coordinates. So let me click on entries that have the atomic coordinates. Reduced it just a little bit, down to 53 entries. And then I want the star high quality pattern. So what I'm going to do is I'm going to remove my check marks from the other quality marks and focus just on the star. Now there's an easy way you can click on them one at a time, or if you hold your mouse down and you just scroll over it, you can remove those. And now I'm down to 16 patterns. So what did we do? Well, we were in the inorganic emphasized, so 500,000. Cement, 1,600. All right. We went down to calcium silicates. We went down to calcium silicates that were Ca2. We went down to atomic coordinates. We went to the star quality patterns. Okay. And at this point, I'm going to open up my search window. So bottom left, click on search. And here are my entries. Okay. And notice the default entries listed here are the PDF number, quality mark, the chemistry. Notice all of them are Ca2S, a name, the 3 despacings for the 3 most intense peaks and in terms of intensity. And then a default that shows up here is SYS, system. that means your crystal system. And you'll see here that some say M. What is M? Monoclinic. What is O? Orthorhombic. How about C? All right. T? H? Triclinic is what? Boom. So triclinic, T. Wait, no, tetragonal was T. Triclinic will be listed as an A. That's a classic term. Anorthic is the original term for triclinic that goes back a little bit. So that's how you designate triclinic. And tetragonal will be T. And if it has an X, unknown. All right. We won't quite say trash. Probably trash light, it depends, because sometimes it's a polymer. The pattern is great, but you're never going to get the crystal structure. Okay? So it does depend, but it's a good point. If it says X, that's going to be one of those caution. Let's take a look at that. What are the comments? Should I be using this or not? Okay, so what do we have here? Well, we see O and we see M. It turns out that calcium silicate, the C2S, is polymorphic, okay? And there's actually a couple of monoclinic phases, and there's an orthorhombic phase, so you do have to pay attention to that a little bit. But okay, this is great. Now you might say, hey, Tom, this is nice. I don't want to have to do this every time I use the database. Can I save this particular search? So what you're going to do is you're going to just hit a Control A, and we're going to highlight all of these. 1 second here. Give me 1 second. And okay, they're highlighted. And anywhere in the area, you would just do your right mouse click and say, I want to add a custom PDF set. And I'm going to call this Bari Cement and say, okay. Now, what does that mean? Well, if I close this search, I see now under custom data set, Bari Cement. So now at any time I want to do a search or I want to look at this data, all I have to do is highlight that, hit search, and those phases are the ones that show up. Okay. Now, earlier question was asked this morning, can someone save their own data to the powder diffraction file? And I'll emphasize the point, the answer is no. It can be saved in the JADE software, and if we have time, I'll mention that. But the reason is that the database, because of our ISO certification, we have to say that you can't go in there and alter it. Now, why would someone want to alter it? Say they wanted to see a phase that they wanted to just change the data a little bit there. Okay, the data has to stay as is. Okay, all right? So that's how you do subfile searches. And just to emphasize a point here, the types of subfiles available, you've got forensics, explosive, hydrogen storage materials, pharmaceuticals is used quite a bit. And under pharmaceuticals, any of these where you see the little plus sign, that means there's also some subclasses. So you can say either I don't want a subclass or I'm interested in excipients. That's where powder XRD is very good. When someone has a pill and you say, oh, I know what the active pharmaceutical ingredient is, and maybe I can call it up in the database. I want to know what other stuff that they have in there with that pill. You can use the powder diffraction to do that, okay? Okay, so I'm going to reset everything. Can I guess questions at that point?
But when you make the reference specified in yourself by a user defined PDF, it is also possible to prefer. If I make a user defined PDF, is it possible to search only on those PDF in some other program like the high school.
So, yeah. I mean, if you, well, okay. So if you've made like this little subfile, directly no, but indirectly yes, because your diffractometer software, EVA, high score, smart lab, you can go in and set some parameters up to say, I'm interested in these particular kinds of phases here, and a similar kind of thing. I will say the PDF database does a whole lot more, okay? But it's designed a little bit different as opposed to the fundamental. I mean, it'll do some phase ID, but you'll have many more searches here. But you can still set up some subfile designations in your diffractometer software. I just can't tell you specific if you could do this exact one or not. Someone here might know.
Find the PDF. I want to find the PDF reference which contain all atomic coordinates to do the ritual refinement.
Generally speaking, you can do that.
You can do that. Thank you.
Okay. All right. So let's take a look at a few of the search categories. So we've highlighted periodic table. Let's just do a few more here. A couple we've already talked about. Excuse me. Okay. So the common one was periodic table. I always like to just do a reset everything just in case. And let's say, for example, we went to the formula name. One of the things to note, if you have, let's say, for example, calcium carbonate, okay? The way it's entered in is you would go CA space C space 03, okay? And we talked about the options here about any formula contains a phrase, must be exactly. Right now, if I leave the default contains elements, it says there's 738 matches, okay? And if I click on the search and look at my search result, it's going to go through the whole database and find the entries that have a calcium, a carbon, and an O3 in it. Now, do you think that since I said it was anything, am I going to get just calcium carbonate? And this is kind of like the issue with the Boolean and search. It'll have those three, but I said it could be anything. So you want to be a little more specific with your search. I'll close this result. And what I'm going to say under my formula now is I want it to be exactly, okay? And now it's going to go through the 500,000 entries, find out which ones exactly have, CA, C03. You're down to 159. And you go through and now it'll print out, it'll basically display the 159. And we heard a bit earlier today, one of the things around calcium carbonate is there are 3 polymorphic forms. So you can have calcite, aragonite, and brookite. Okay. Oh, I'm sorry, that's TiO2. You can have, yeah. And so you can look and you can see here that in fact I do have the system, meaning different crystal systems, consistent with the polymorphism. All right. Now, the one thing I haven't shown you yet is, okay, great, Tom, you got the search result. What if I want to look at that PDF entry? All right, there's 2 ways you can open up the entry. You can either highlight a particular entry and you can say open that PDF card, or you can double click on the entry. And I picked this one with the blue star for a reason. Let's open that up. So you click on it and that PDF entry will open up, and you'll notice that within a search menu, if you say, well, I want to look at the one before it, just click on the little arrow right here, and you see the one that was before it. Go back where you were, go to the one after. So you can look at a couple of these to see how they compare. Now, this particular one had a blue star. What's the blue star mean? If I go in my data entry and I look at the experimental tab, I see that it was data collected with an internal standard. And that means that we have confidence that the data are a bit better, higher in quality in terms of its peak position. So the blue star is just an indicator internal standard was used. Okay. Now the other thing here with this one, you can look at the structure, and if you have the atomic coordinates, what can I do with that? Well, I can use these in some kind of refinement or whole pattern fitting program. How do I do that? And what you're going to find is in the web version that you're going to use, it does not have this export function. And the reason is we were teaching a class, we taught a class overseas in another country, and a couple people thought that the export function meant that they could try to download the whole database. Okay, and that's not the intent, okay? But if you purchase the database, you don't need to download it. So, okay. So anyway, what do? So under the export function, if you look at that, you have a couple of options. One option is you can export the data in a CIF format, and the CIF can be read by anybody's program. A special request came from Booker to put an STR format so it can be read right into Topaz. And you can also basically export as an XML file as well. Okay. You also, if you wanted to, some people like to print a PDF entry, and they can print it out and just have a record of it if they would like to. Okay. But so that's the nice thing is that, and each instrument company is a little bit different. Some of them, when they build their index file, have already added the atomic coordinates from the database, so you don't have to do the export, and some you need to do that particular step, but it's easy either way. Okay, so when you open Jade, you're going to get something that looks like this, okay? And built into it, with what you have in the online web, you're going to go to, there's some default demo files here, and the purpose of these is to have some things you can work through and understand what's going on, okay? And not try to find some crazy analysis, all right? But what I do want to note is that you're going to go up to the start and click on open a new folder. Now, for me, on my desktop, I have a BARI folder, okay, here, but on your web, you're going to look for something on the side that will say Documents. And when you click on Documents, there's going to be folders there that have the data you want to look at. Okay? And again, I'll be here a couple days. You want to see me, help you get started, I'll help you get started. Okay? All right. So I've got an example, a demo file here, and here's a particular PDF entry. So I've just clicked on it and the entry opens up. Now, one of the things you're going to want to do is you're going to want to decide which database do I want to use for doing my identification. So what happens? In these, in your software packages, it doesn't matter whose it is, they all do the same thing. They take the powder diffraction file database and they extract part of the data. They make an index file. They don't extract everything because it's big. And you know, your phase ID, people want results now. They want to hit a button and they want the answer before they hit the button. I mean, right? I mean, people want to go quick, okay? So what is generally extracted will be the chemistry, D-space data, intensity data, may or may not include the indexing, may or may not include the atomic coordinates, and it kind of stops there. All of that other information, the metadata and things like that, typically is not pulled in, okay, just because it's too big of a file. So what you have is you're going to want to say which database. So one of the things is databases are preloaded, but we had a question earlier today about, can I make my own database? And so when you go up to the database tab, there's something here called create a user database, okay? basically for search match and whole pattern fitting, this is where you would set up your particular entries. And you don't have to have the atomic coordinates, but it's nice if you do. Well, you need it for whole pattern fitting. But if it's for phase identification, you're looking at a pigment and there's 9 known polymorphs and you just want to fingerprint them, you need the D's, I's, your chemistry, and then it will assign a number for it, okay? So you can build your own database. But here we have databases in the bottom right. We have a list of what we have. There's sort of a default minerals. We do have the American Mineralogist data in here. And then we have data that's been derived from the powder diffraction file. For quick purposes, I'm going to just, for this first example, just refer to the MDI 500 minerals, okay? That's just simple identification. Okay, so we have a couple options here. And so one of the things that you want to pay attention to, we heard earlier in the presentation before mine, one of the things that you need to be looking at is your peak identification, your peak positions. Bad peak positions, bad phase ID. So you want to make sure your peak location is good. And sometimes these peak search algorithms miss a peak, or they put a peak in there that isn't there. Why? Generally speaking, there's a second derivative method for finding a peak, and if the peak's a little bit noisy or it's a little bit low in intensity, it may miss a peak, it may add a peak. So you do want to go through, and in here, there's a little icon here that's called Cursor Edit Peaks, and you can go in and decide if you want to add a peak or remove a peak. All right, but this peak search looks pretty good. Look at, I'm going to sort of just scroll over this area here. Look at this region right here. So I've got 3 peaks here, and look at peak number 2. They look a little bit broad compared to the others. So that's one of those things qualitatively says something to me that maybe there's at least more than one phase in this sample. One might be a little bit larger crystallites, the broad peak a little smaller crystallites. And this is without any ID, but just sort of visual things that you should be looking for, okay? When you want to reset your pattern, there's a little icon here that says full or last range. And if I click on that, I'm back to where I was. Now, I'm going to do, I'm happy with my peaks. I'm going to look at my phase ID. Now, with phase ID, you can, if you want, you can enter in some chemistry if you know chemistry. I think pretty much everybody's software does this. You can have some fluorescence data, or I know what I'm working with, or I think I know what I'm working with. You can enter some chemistry data if you want. And again, depend upon the particular software you're using. You might even know something about some unit cell information, what instrument it came from, etc. All right. So other thing is I can look at, generally you have some parameters you can set. Do I want to force it for a single phase? Do I have severe preferred orientation? If I'm not getting a match, I might have an orientation issue. Exclude metallics, exclude organics. So different things you can do here, okay? I'm going to just go ahead and do the search. And how do I do the search? There's a little search match icon here. Click on the search match. It's going to go through to do the phase identification. And in this case, it's letting me do this one step at a time. I'll show you an automated method in a moment. So in this case here, the first phase it's trying to identify is rutile, and I look at where it has placed the rutile peaks, and I'm pretty happy with that. Now, earlier we had a question here about what do you use to say is the criteria good or not? And we talked about figure of merit. Everybody has a different mathematical equation for their figure of merit. This one, goodness of match, which was in PDF5 Plus, it's a perfect match is 8,000. It looks at 8 peaks. Most may look at 3 peaks or maybe a whole pattern. And how does a pattern match? So in this particular case, the smaller the figure of merit, the better your match. Okay, you just need to know what's there. So in this case, The rutile, I like the rutile, so I'll click yes on that. Next one it goes up to is hematite. Hematite's an iron oxide. I'm looking at the peaks that are associated with the hematite there. I like the match of the peaks, so I'm going to say okay. And then the last one that's left is the anatase. Now, here the case with the anatase, notice my figure of merit is a little bit high, but yet if I look at it, the peak positions look pretty good. What's going on? This is that issue about the peaks are a bit broad. So it's saying, hey, maybe we should be using integrated intensity instead of peak intensity for getting the better match in this particular thing. But the positions are good, and I'm okay with the position. And if I click on that, and the little thing went beep there for a second, no remaining peaks. In other words, it didn't have anything else it could match. Now, one of two things has now happened. I either did a really good job or I did a really bad job that looks good, okay? You know, as the user, you still need to look at the results and say, does this make sense? Now, the sample is identified as a red pigment, and iron oxide, interestingly enough, if you look at iron oxide, it's so dark red, it almost looks black, but when you grind it to a powder, it's reddish in color, alpha phase. That's the key, alpha phase. And TiO2, that's found in paints, is sort of the filler that makes your paint have, so it's not transparent. So I'm pretty happy with the phases, okay? We heard comment about RIR, reference intensity ratio, and that's where people either experimentally, years ago, Chun from Sherwin-Williams worked at a paint company, and he chose aluminum oxide. I don't know why, but he would mix samples 50-50 with aluminum oxide and come up with these ratios of peaks. And then when he had a mixture, he used this matrix flushing technique to try to quantify what was in his sample, okay? And it works well if A, your samples are randomly oriented, crystalline, and you know what's in there, okay? Where it will fail is if you have preferred orientation or if you have a lot of amorphous material, okay? So it's a good semi-quant method, and that's why we refer to it as semi-quant, okay? And for years, people used it because it was easy to use and computers weren't powerful enough to do read-felt refinement, but today your computers are more than fine for doing read-felt refinement. The complexity of read-felt refinement, as you're going to hear more tomorrow, is there's a lot of parameters you can adjust so you can make something fit. Is it the right thing? Okay? All right. So I'm going to clear things. When I want to do that, I move my cursor sort of in the bottom left of the plot, right mouse click, and I'm going to say erase things. So I've erased what I've got. And I showed this example earlier where on my phase identification, there's this thing called one-click analysis. Now, one-click analysis is okay once you understand your system, okay? If you know what's going on. This is kind of, Robert was talking kind of the quality control, particularly if you're running the same thing again and again and again, you establish some parameters and it just keeps cycling through those parameters. It does pretty good, all right? So caution that, look at your data. But in this case, if you do the one-click analysis, but what it does is it goes through and it says, I think these are the phases that are there. It just did the read-felt refinement for you. And if you look at your read-felt results, you can see the parameters that were adjusted. The positive of this, I can cycle through samples, boom, 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 boom. I think we heard Robert say he didn't like a certain graduate student, so he gave that graduate student 500 samples to analyze, okay? At this point, the graduate student is now drinking his Peroni, okay? Sitting by the curb, enjoying life, okay? If you know the system, all right? So you could say, okay, here's my quantitative analysis. I can look at things here to say, does this make sense or not? And I might need to make an adjustment. And in fact, I would make an adjustment here. unfortunately, we don't have the time, but one of the things I would show you how to do is you need to set up your instrument profile, okay? And I have the data to show how to do that, but that's what you would do. You need to have your instrument profile set up properly to really do good quantitative refill, okay? So we're going to do one last example, and then we're out of here. Okay. I'm going to erase everything, and in fact, I'll just clear my plot. And I'm going to go to another example here. And this is very similar to one that we heard in the talk before mine. It's a common problem, and it relates to preferred orientation. In fact, similarity in the patterns here, okay, kind of thing. So again, we can go through this exercise to say, let me do the phase identification, and I will do my search match, and found 4 phases. Okay, I found the 4 phases fairly quickly. All right, why? Well, it's good data, and the phases give good diffraction patterns. Okay, you get into some really messy patterns that have multiple peak overlaps, not so simple for the analysis. All right, so I look at this and I say, well, this fluorite is in the sample. I like that pattern. I like the zincite in the pattern. Brushite, and I'm going to say something's funny with the brushite in a moment here. Let me make my a little broader here. This peak here is the initial brushite peak. And on a relative intensity basis, the peak that should be 100% was identified. This peak should be about where the red marker is, and yet it's not. What's it tell us? Well, we have something else going on in the sample. So if I double-click on brushite, I can see sort of PDF type data, and I can see that that first peak is the 001 peak. So that tells me I probably have some kind of preferred orientation in my sample. Okay? Now, when I want to do quantitative analysis, this is a case where the RIR method won't work because I've got all this orientation, okay? So what I'm going to do is I'm going to clear my data, and I'm going to say to myself, is my one-click analysis smart enough to identify preferred orientation? We know the 4 phases. We're okay with that, right? So I'm going to click on one-click analysis. It immediately found the phases. And now, with just the first pass, it's done the refill refinement, and it's done something with that peak. In other words, somehow or another saying, wait a minute, you got orientation here. I'm going to put a correction in there. Now, hopefully, you will still look at the data and say, let me just check and make sure this makes sense, all right? So I'm going to take a look at the result, and you'll notice on my brushite phase, it put a PO by it, meaning that it found high degree of preferred orientation, and it made a correction for that. This is where you look at the data and decide, do I agree with that? Do I need to refine a little bit further? Because this is a point now where you might do some additional work, okay? But I do want to focus on the brushite for a moment, because one of the things that it did here was it turned to spherical harmonics to be able to model the orientation. And if you look at the simulated figure, what it's saying is the brushite is needle-like in structure. And in fact, that's correct. Now, the way it was able to do that is it looked not just at one peak, but it looked at all the peaks and saying, hey, wait a minute, how do I get this peak intense, this peak less intense? I must have a certain particle morphology.
How can I get the figure?
How can you get that figure? Okay, so in the results of the whole pattern fitting, you'll see down here where it's got about orientation, there's a little
shape figure. This one. Sweet.
Okay, well, okay. So you want to do, well, So this one probably doesn't have the orientation, but if you click on the little icon right above, right there, yep, see? Click on the little right there, next to the little, right on that little figure right, yeah. Can you just show them? Yes. Yeah. Yeah. So basically, so what you would do. What you would do is you would click on the little icon here, and when you open it up, that's how you would see the data that's been gone through in terms of this first refinement. Then if you need to adjust parameters, do you need to put an amorphous component in there? Okay. You have that option to add an amorphous component. Do you need to change your background? Do you need to change profiles? Those are the things that you could do after you've done through this. But the automated type search is very good for quality control on well-defined systems.